Okay, so welcome to Math 355 Abstract Algebra. This is lecture 9, or it might be lecture 11. I have to check and see how I'm counting the lectures from last week. And what we want to do today is finish off chapter 3, rings and homomorphisms and fields. And then next class, we will do applications of group theory and we'll prove why RSA works. So for today, let's start off with some definitions. So definition 326, let R be a commutative ring. We will always be working with commutative rings. But it is possible to have a ring that's not commutative. That's why we need to say this. When I say a ring is commutative, what does commutative mean with respect to what? With respect to multiplication. So an ideal of R is a non-empty subset I that's contained in I, and it has two properties. If you take two things in I and add them, you get something in I. And if you take something in I and something in R and you multiply, you get something in I. So notice that the second condition is a bit more generous than you might have expected. What might you have expected the condition to be for an ideal, for multiplication? Yeah, it has to be two elements in I. And it's here, it's an element of I and it's an element of R. And so in this situation, we do not require R to be in the ideal, okay? So in this setting, I'm also looking at R times A. Why don't I look at A times R? Why is it the same thing? Because it's a commutative ring. So we assume that we have a commutative ring, and so I don't have to worry. R times A is the same as A times R. And it's important to note that if we take R equals 0, well, 0 is then going to be an I. So as long as I is not empty, I will always contain 0. Then the question becomes, what else must the ideal contain? There are two ideals that you should always be able to tell me for a given ring. These are the no-brainer, obvious ideals. What are they? Everything, right? If you take I to be R, then because R is a ring, it's closed under addition and it's closed under multiplication. So we know that R is always going to be an ideal. What else will always be an ideal? The additive identity, just the 0 element. 0 plus 0 is 0. Anything times 0 is 0. So the question is, when do we have a ring that has more interesting properties? Okay, so what are our go-to examples of rings? I'm sorry? The clock, and what else? So go-to examples. We have the clock, and what else do we have? If you want, you can view it as a very, very big clock. The integers, right? These are our go-to examples, the integers and the clock. So let's try to imagine what the ideals might be like for the integers. Okay, can you give me some element in Z? So let's take R equals Z, and let's let I be an ideal. Okay, so let's try to figure out what are the possible candidates. So the ideal is non-empty, so there has to be at least one element in I. We know there's one element, we know 0, right? We know 0 is an I. If A is an I, so is minus A, right? We just multiply by -1, and -1 is an integer. So without loss of generality, let alpha be the smallest positive element of I. If no such alpha, then I is just the element 0. So if I have a ideal, the ideal has to have at least one element, 0. The question is, does it have anything else? If it has something else, then I can look at all the positive integers that are in I, and I can choose the smallest one. And let's call that alpha. So now we know alpha is in I. Can you tell me something else that has to be in I? So alpha is in I, what else must be in I? 2 alpha, and what else? Okay, a negative alpha. So all multiples of alpha are in I. So all multiples of alpha are in I. Is anything else? So we want to show that nothing else is in I. So imagine there was something else. Assume beta is in I, and beta is not a multiple of alpha. Then how can we write beta if it's not a multiple of alpha? Good. So let's do maybe m alpha plus r. And what do we know about r? It's smaller than alpha. It's not equal to alpha. What else? How small can r be? So could r be 0? What would it mean if r is 0? Strictly greater. If r equals 0, then beta is a multiple. So we know that r is not 0. But beta is an I, m alpha is an I. So since beta and negative m alpha are an I, then r, which is beta minus m alpha, is an I. But r is less than alpha. Contradicts alpha is the smallest positive integer in I. Thus, I is all multiples of alpha. Minus 2 alpha, minus alpha, 0, alpha, 2 alpha, dot, dot, dot. So we now know the entire structure of the ideals of the integers. They have to be multiples of a fixed number. Okay? And the way we found this out is we said, well, look, either I is the 0 ideal, which is really easy to understand, it only has one element, 0, or it has more elements than 0. If it has more elements than 0, since the integers are ordered, there has to be a smallest positive integer, which is an I. Call that alpha. Clearly, all multiples of alpha will be in the ideal, because the ideal has to be closed under addition. It has to be closed under multiplication of things in R. What if there was something else? And then we said, well, if there was something else, we could then show that there's a new element in I, which is strictly smaller than alpha, which is a contradiction. So we completely understand the structure of the ideals of R. We can, of course, then try to apply and understand what might be the structures in the clock rings. And that's, the next thing that, we'll be looking at later today. The next slide is, not surprisingly, very much related to what we just did. So let R be a commutative ring, let C be an R. The principal ideal generated by C, and we have two ways of denoting this. We denote this either as C times R, or C in parentheses, is the set of all multiples of C. And by multiples, I mean multiples by things in R. Okay? So we've seen something like this before, but we've looked at clock groups. For example, 12z would be, dot, 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 minus 24, minus 12, 0, 12, 24, dot, dot, dot. We had stuff like this. And so what we just noticed is in Z, every ideal was principal. In Z, every ideal is principal. That may not be true in other rings. It's really nice if a ring is principal. There's some generator. Does the generator have to be unique? Instead of looking at multiples of 12, what could I look at? There's something else you could look at. Negative 12. I could look at multiples of negative 12. Those are the only two things that would work. This is the same as negative 12z. And really what's going on is I have two units. I have two elements that are invertible, 1 and negative 1. And so you can look at other rings and try to ask what might their ideals be. So for example, if we look at the clock group Z mod 12z, look at I equals 048 on the clock. Because I'm using I, what should this be? It should be ideal. If it's not an ideal, I am using horrible notation, right? It's possible. I haven't taught this class in over 15 years. I might be using bad notation, but if you see I, you should be thinking ideal. When we're doing group theory, if you see G, what should you be thinking of? Group. And if you see H, what should you be thinking of? When we did group theory, what was H? Subgroup. It doesn't have to be a subgroup, but if you are doing something and H is not a subgroup, shame on you, right? If I have something and I'm not sure if it's an ideal, I should use S for set. And then later I can prove it's an ideal and justify the use of the letter I. All right, so is this an ideal? 048 on the clock. If I take two elements of this and add them, do I get something back in I? Yeah, 4 plus 4 is 8. 8 plus 4 is 12, which is 0. 8 plus 8 is 16, which is the same as 4. If I multiply by anything in the clock, any 0, 1, 2, 3, all the way up to 11, is it still going to be, yeah, these are multiples of 4. These are multiples of 4. It is an ideal. Okay. Do you think this is a principal ideal? Is it generated by multiples of something? I did, yes. It is principal. It's just multiples of 4. Is it possible to extend this and get some bigger ideal that's not all of Z mod 12Z? Can you find a bigger ideal that contains this that's not everything? So here's our ideal, 0, 4, 8, basically the multiples of 4. Here is, Z mod 12Z. Yeah. So 0, 2, 4, 6, 8, 10. That would be strictly greater than 0, 4, 8. It would contain it, but it would not be the whole thing. So we can add 2 and everything that comes with adding 2. So if we join 2 and look at, when I add 2, I'm not just adding 2, I'm adding all multiples of 2, and then 2 plus everything in I, and then 2 times anything in I. If I look at everything that I have to do to make it an ideal, I don't get all of the clock. But there is another number I could add, and I would get everything in the clock. What could I add? I could add 1. What else could I add? 3. What else? 5. What else? 7. So if we add any odd number, add any odd, and then all needed, sums and products to get an ideal, we get everything. And the reason is, for example, if I add 7, note 1 is 7 minus 6. If we add 9, note 1 is 9 minus 8. So we can always show that 1 would be in the ideal form from adding anything. Oh, sorry. I'm not allowed to use 6. Right? Sorry. Because we have the ideal of 0, 4, 8, not 0, 2, 4, 6, 8. So how can we show that we can do 7? I'm sorry. If we add 7 and we have 6. So I can't do that. So if Q is odd, we only have multiples of 4, then what's the GCD of Q and 4? 1. So by the Euclidean algorithm, there exists X and Y such that XQ plus Y times 4 equals the GCD of Q and 4 equals 1. Since XQ and Y4 in the ideal, so is 1. And thus is everything. If I gave you something like 7, I could say 1 is equal to 8 minus 7. If I give you 9, I have to do a little bit more work. How can I get 9? Oh, that's just, 1 is just now 9 minus 8. So it's really not that hard. If I give you an odd number, it's either 1 more than a multiple of 4 or 1 less than a multiple of 4. And so I can figure out which way to do the subtraction to get 1. So for this particular problem, it's not too bad to do. But what's nice is this gives us a nice shout out to the power of the Euclidean algorithm. We used the Euclidean algorithm when we did group theory to show that if we have a prime, then anything that's relatively prime to p is invertible on the clock with p hours. And we're basically using this again here. Okay. So the next one is let R be what kind of ring? Commutative. We have to keep saying it. There are rings that are not commutative, but we will only be considering commutative rings. And let I be an ideal of R. And for each element A in R, the coset of A is the set A plus I, where that's going to be all things of the form A plus C as C ranges over I. Okay? So it's possible that if I give you a coset, there could be more than one representative of the coset. And we have to figure out how are we going to define operations on cosets. So I will let you be the supreme deity. You may choose how do you want to take the coset A plus I and the coset B plus I and add them. What would you like that to be? What would you like A plus I plus B plus I to equal? You get to choose. You weren't able to choose for the derivative of a product as the product of the derivatives. You couldn't choose the derivative of a quotient as the quotient of the derivatives. I'll let you choose. What would you like a plus I plus b plus I to equal? A plus b plus I. Good choice. And for multiplication, if you have a plus I and you multiply by b plus I, what would you like that to be? AB plus I. So for example, let's say we take R to be the integers, and let's take I to be multiples of 12. Then 8 plus 12z plus 7 plus 12z, what would that equal? So what would 8 plus 12z plus 7 plus 12z be? It's 15 plus 12z. And what's that the same as? Or what should that be the same as? 3 plus 12z. And the idea is we should have more than one ways of representing, that we have multiple representatives. If I look at all multiples of 12 and I shift them by 3, or I look at all multiples of 12 and I shift them by 15, it's the same set. So we really want 15 plus 12z and 3 plus 12z to be the same, and they are. It's just two different representatives. So when I say a plus I plus b plus I is a plus b plus I, I'm not saying a plus b is maybe the minimal representative or the representative I would want to use. To some extent, I might want to reduce a plus b by some element in I. And implicit in this is the following fact. If I is an I, then what do you think little I plus big I should be? I. Proof. If X is an I, then I plus X minus I is in I plus I, since X minus I is an I. So we're basically just adding 0 in a clever way. I want to show that if I take any element little I and big I, then the coset little I plus I is the same as I. And the reason is that coset is everything of the form a plus something in I. Or here it's going to be little I plus something in I. And so since X is an I, am I allowed to do this? Yes. Do we know that X minus I is an I? Yes, because little I is an I, and we've assumed X is an I. So you give me any X in I, I've just shown that X is in little I plus I. What about the other direction? Is I plus I contained in I? Yeah, right? Because I is closed under addition, so this is clearly going to work. So just before we start analyzing, the sums and products of cosets, it's good to just get a little feel, some intuition. And the first thing was looking at, if we add two examples in our clock setting, which we kind of understand, we see that we have more than one possible representative. And then the second, which will be useful later, is if we take either A or B to be something in I, this is effectively the identity element under coset addition. If I take little I to be an I, then little I plus I is just I again. And I can just do a little shift like this to show everything is fine. All right. So now we need to show everything is well behaved. So let's explore one. So we want to show that A plus I plus B plus I is A plus B plus I and vice versa. So in this direction, let's let let's take some element X in A plus I plus B plus I. So we can write X as A plus something in I. And I'm going to choose to write it C sub A plus B plus C sub B with CA, CB, and I. There's lots of notations you could use. I could have used C1 and C2. I could have used C and C prime, C and C tilde. Why do you think I'm using a subscript A? Yeah, to remind myself, this is the choice that's coming from A. And so because X is in A plus I plus B plus I, it's got to be something in the first one, which has to be A plus something in I. Let's call it C sub A. All right, what should we do for that sum? We want to show that this is equal to A plus B plus something in I. So remove the parentheses, and once we remove the parentheses, what should we do? So which things do you want to move together? Yeah, so we'll move the C's together and the A's together. So we can write this as A plus B plus CA plus CB, but CA plus CB is in what? It's in I, because I is an ideal. Call this C sub A plus B. So this is A plus B plus C sub A plus B, which is in A plus B plus I. So that finishes that direction. Okay. Now we need to show the other direction. Let's assume X is in A plus B plus I. So X is equal to A plus B plus some element C, call it A plus B, with C A plus B in I. So we want to show that we can write this X as something in A plus I plus something in B plus I. So we want to write X as A plus something plus B plus something, where the first one is in A plus I, the second one is in B plus I, and their sum is A plus B plus CAB. So any thoughts about what I could put in? Good, I can put in 0 and CA plus B. And that's going to be an A plus I plus B plus I. So 0 is the easiest choice. What if I decide I don't want to use the easiest choice for once? What could I put in? What if I choose some C in I over here? Then what would I do? Then we just subtract. I'm basically just adding 0. And that's also an A plus I plus B plus I if C is anything in I, as C A plus B minus C is an I, as I is an ideal. So the easiest choice is to take C equals 0. But I can take anything I want and just combine it like this. And so this is how we define addition. And you can simply show that if we define multiplication, everything is going to be good. The next, the next slide is talking about just formalizing this and showing that it really has the properties. So as always, what kind of ring is R? Commutative. So R is a commutative ring. I, as always, is an ideal of R. The A plus I and A prime plus I be two cosets. Then the two cosets are the same if and only if their difference is an I. And essentially, that's what we just showed a moment ago. That if we take anything in I, then the coset of little I plus big I is just big I. What this is saying here is the only time you have a coset equal to I is if the representative is an I. Addition and multiplication of cosets is well defined in the sense that it doesn't matter which element of the coset we use in the definition. Addition and multiplication of cosets turns R mod I into a commutative ring. So what's nice here is that we're basically saying that two elements are going to be equivalent if they differ by something in I. So think of this as, we're looking at things on a clock, and we say two things are the same if they differ by a multiple of 12. Well, instead of being a multiple of 12, it's now just something in I. We're lucky on the clock that everything is a multiple of 12. This is a really nice ideal. It's a principal ideal. It's generated by multiples of 12. We might have a more complicated ideal that's not principal. That's fine. We can still do something like this. So the proofs of these are all pretty much the same. I'll just do the second one. Since we did addition before, let's do multiplication this time. So proof of B multiplication. So we have to show that addition and multiplication is well defined in the sense that it doesn't matter which coset we have. So imagine A plus I equals alpha plus I. Then we can write alpha as A plus what? So if the two cosets are the same, how must alpha and A differ? By something in I. And let's call that C sub A. With C sub A and I, this is from part A. So from part A, two cosets are the same if and only if their difference is in I. Okay, and similarly, if B plus I equals beta plus I, then we can write beta as B plus CB with CB and I. So now we have to show that if we multiply the two cosets, it doesn't matter. I can use two different representatives and I will get the same thing. So we have to look at alpha plus I times beta plus I. That's going to be, by our definition, alpha beta plus I, which is A plus CA times B plus CB plus I. So this is going to be AB plus, I'll do it as ACB plus BCA plus CAB plus I. Now we're trying to show that it doesn't matter which coset representatives we use. So we want to show that this equals AB plus I. It would be wonderful if the quantity in green equaled what? What would be the easiest case? If that equals what? Your dream world, 0. If it equals 0, then we're done. But it's probably not going to be 0. But from part A, when are two cosets the same? When their representatives differ by something in I. So all we have to do is show that this is an I. If this is in I, then above is just AB plus I. Oh, it's right. It's not CAB, it's CA times CB. So as CA, CB are an I, that implies ACB is an I, BCA is an I, and CACB is an I. Thus, the sum is an I. And we're done. Okay. So this is how we proved it. This proves that multiplication is well defined. What we could have done, more interesting one, alternate proof. Since section 2 normally goes a little bit faster than section 1 because I've already practiced on section 1, I'll say instead we could look at A plus I and B plus I versus alpha plus I and B plus I. Change one at a time. So as an aside, rather than changing both of them, we could just change the first factor to an equivalent coset and show that that's the same, and then change the second factor and do it in stages. And then that would make the calculation a little bit simpler. There's no need to do that, but it's not bad to just quickly remark that. Okay, so now proposition 334. Let R as always be a commutative ring. Let I as always be an ideal of R. Then we have a natural map from the ring R to the new ring R mod I. And the map takes A and sends it to A plus I. Okay. I actually was preparing this lecture from an earlier draft of the book, and in the earlier draft of the book, there was a typo and it sent A to A plus R. And you know that can't be right because then the ideal I is not playing any role in the mapping. And so, when I see I've got a commutative ring I, I have an ideal I, that has to somehow play a role in the map. So when you're looking at things, you want to be able to quickly do some quick sanity checks. Is everything reasonable? Part B, let phi from R to R prime be a ring homomorphism. So let's see. One of the advantages of doing the lectures like this is I should be able to just quickly go back. Yes. And here is the definition of a ring homomorphism. A ring homomorphism has three properties. It sends the multiplicative identity to the multiplicative identity. Phi of a sum is the sum of the phis. Phi of a product is the product of the phis. So this is what it means to be a ring homomorphism. You have to satisfy these three properties. And then the kernel is the set of all elements that are sent to 0. It's not too bad to show that 0 has to be in the kernel, so the kernel is not empty. All right. So now, in terms of what we're doing, in part B, we have a ring homomorphism. And so the first part 1, is that the kernel of phi is an ideal. So the set of things that are mapped to 0 is an ideal. The homomorphism is injective if and only if the kernel is 0. And then finally, writing I sub phi for the kernel, there's a well-defined injective ring homomorphism from R mod I phi to R prime, defined by sending A plus I phi to phi of A. And so what we're doing here is we're taking the ring and we're modding out by all the things that are sent to 0. And when you do that, you then get a ring homomorphism. So as always, I am a huge stickler for good notation. Why do you think we're writing I sub phi for the kernel of phi? So why do you think where does the letter I come from? It's an ideal. And where does phi come from? The map. So when I write I sub phi, I should quickly be able to look at this and say, oh, okay, this is the ideal generated by phi. What's the best way to generate an ideal from phi? Look at the kernel. It's just a good name for it, so I can quickly glance down and see what's going on. I'll prove just B1, and I'll leave the rest for you. Again, if you have any trouble, come to me, talk to each other, talk to the TA. So we'll prove B1. So we must show that the kernel is an ideal. So must show for all A, B in the kernel of phi, and for all little r in the ring R, A plus B and R times A are in the kernel of phi. That's what it means to show that the kernel of phi is an ideal. It's got to be closed under addition. So if I take two arbitrary elements, then their sum is in the set. And it must be closed when I multiply by anything in R. So the first is, what would be phi of A plus B? What would that equal? So what would phi of A plus B equal? And phi is a ring homomorphism from R to R prime. Good. And so why is it phi of A plus phi of B? Because it's a ring homomorphism. And for ring homomorphism, phi of a sum is the sum of the phis. But what does phi of A equal? So A and B are in the kernel of phi. So what does phi of A have to equal? Has to be 0. Yeah, the kernel of phi is the set of all elements sent to 0. So it's got to be 0 plus 0 as A, B are in the kernel of phi. 0 plus 0 is just 0, and that's in the kernel of phi. So we just showed sorry, this one. Therefore, A plus B is in the kernel of phi, because we just showed that A plus B is sent to 0. So now we need to do the next part. So now we need to look at phi of A times R. What would phi of A times R be? So we have a ring homomorphism. So what would phi of a product be? The product of the phis. Oh no, I wrote A times R instead of R times A. It's commutative, I can be careless, right? So that's phi of A times phi of R, as it's a ring homomorphism. And phi of A is just 0 times phi of R, and that's just going to be 0. Therefore, A times R is in the kernel of phi. And again, I can be careless because it's commutative. So the other parts are proved very similarly. Strongly urge you to try to do this. The further you go in mathematics, the more important it is to do lots of problems, to put in the details in the proofs. If you've ever tried to learn how to program, there are some people who try to learn how to program just by reading books. Every time I try to do that, it doesn't go well. You have to sit down, you have to roll up your sleeves, you have to type, you have to code. Okay. So let's try to do some examples and find some rings. So can somebody give me some examples for rings? We have our two go-to examples. Clocks. What else? Integers. Can somebody give me another example? Quaternions. So we could do quaternions. We could do Hamiltonians. Can anybody give me another example of a ring? I'm sorry?
What's Hamiltonians?
It's an extension beyond the quaternions. Let's skip that. Sorry, probably the octonians, but then you lose association. No, skip that. That's not necessarily correct. Let's just leave it as quaternions. Can somebody give me another example of a ring? Matrices. So let's let example Let's let M2 of Z be the set of all matrices A, B, C, D, where A, B, C, and D are integers. Is this a ring? Yes. So this is a ring. Can somebody give me an example of an ideal? The zero matrix, right? Can somebody give me another example? The whole ring. And what do you think the question I'm going to ask is? Yeah, is there anything else? So one of the disadvantages of teaching the same class twice is it's hard to feign ignorance in section 2. But I deliberately did not prepare, because I don't really care that much about this now. I did not prepare deliberately for section 1, so I was somewhat on the spur of the moment. Can you think of an ideal, a set of matrices that's going to be closed under addition and closed under multiplication of anything in 2 by 2 matrices? Okay, so you want to take your ideal to be multiples of the identity. So if you take your ideal to be multiples of the identity, then when you multiply by an arbitrary element of M2 of Z, you just get that element. So your ideal would then contain everything. But you can fix it though. If you take, say, if you take your ideal to be maybe created by maybe what you get if you start off with 2 times I.
Yeah, I mean, multiples of identity terms.
Right.
Element of Z.
Right, but the identity is a multiple of the identity. And so if you include the identity, you then have everything. Right? Yes, because an ideal, right? An ideal, right. But so let 2 times I, oh, I don't want to write 2 times I because I is used for ideals. Let's 2 times the identity matrix 0, 1, I'm sorry, 1, 0, 0, 1. So the matrix 2, 0, 0, 2. Yo. Shows after algebra that we get your matrices can be of the form, 2A, 2B, 2C, 2D. So I equals the set of all matrices, 2A, 2B, 2C, 2D, A, B, C, D, R, and Z. It's closed under addition. It's closed under multiplication by R in M2 of Z. Is this an ideal? Yes or no? Does everybody agree yes? This is an ideal? Are you happy that this is an ideal? If I take 2 things where every element is even and I add them, then every element is even. And if every element is even, if I multiply it by anything, I'm still going to get all the elements are even. So does everyone agree that this is an ideal? Yes? Let's get a sense of how comfortable you are. Will you bet your entire grade for the course right now? If this is an ideal, you get an A+. If it's not an ideal, you get an, this is really, you can't get an F, you get an E. How comfortable are you? Will you take the bet? Who else wants to take the bet right now? entire semester. Still February, still March, before spring break. Would you like to see the definition of an ideal again, just to make sure you're comfortable? Do you still want to take the bet? I'm sorry? Why not? Commutative. Ah, yes, I got it by you. Yes. I feel like a hockey player or a soccer player getting past the goalie, right? Got this by all of you. And I emphasize it, this is recorded. I said, as always, commutative ring, as always, commutative ring, as always, commutative ring. See how easy it is to implicitly not check things. Okay? Technically, the answer is no. No, as it's not commutative. Now, do you think we could generalize the notion of an ideal to a situation that's not commutative? And maybe we would have to, perhaps. But what we have requires commutativity. This is not commutative. This is an example of a ring. And I said very carefully, let's look at examples of rings. This is a ring, but it's not a commutative ring. So when we're talking about looking at ideals, we can't use this. Okay, so this is just a really good example of how careful you have to be and how constantly you have to be on guard. Now, of course, what's nice is if I were to make another bet with you, you would all be so terrified that you probably wouldn't try anything. Now, I'm not willing to take the bet now. All right, so let's look at some examples of ideals. So we've talked before about the integers, and we've seen that the integers are principal, that if I take any ideal of the integers, there is some element that generates everything. So if R equals Z, then the ideals are principal. And they'll be of the form like alpha, like this. And I could look at clock groups. We've done clock groups. I could look at like, Z mod 12Z. I could look at, multiples of, 4 or 6 or 3, lots of things I could do. And then one of the questions we can always ask is, if I give you an ideal, are there larger ideals? So for example, if I give you R equals Z, and I give you the ideal that's multiples of 12, is there any ideal larger than 12, but less than all of Z? So can I find an ideal that's larger than 12, but not all of Z? Multiples of 4. What else? So I wanted to contain the multiples of 12. Right? So I want something larger than the ideal that's multiples of 12, but smaller than all of Z. 3, 4, 6, you're missing something. So you started with 3. What could you start with? Well, if you have 1, then you get all of Z. 2, right? I could have multiples of 2. I could have multiples of 3. I could have multiples of 4. I could have multiples of 6. Anything else? Could I have multiples of 5? No. Could I have multiples of 7? No. 8? No, because 4 would not, 12 would not be a multiple of 8. Multiples of 9? Nope, 12 is not going to be a multiple of 9. So I have, several different ideals that are larger than 12, but smaller than Z. What if I take R equals Z and P prime? Is it possible to find some ideal J that's larger than P, than the ideal that's generated by P, but smaller than all the integers? Okay. So assume we have some x in J, but x is not in P. Okay. So we want to show that J now has to be all of Z, that if we have some ideal that contains all the multiples of P, then it has to be all of Z. So if x is not a multiple of P, what do we know about x and P? We don't use the word mutually. It's close.
Yeah.
Think of Einstein. Co-prime would work, relatively prime.
Relatively prime.
So x and P are relatively prime. So the GCD of x and P equals 1. So you should have a Pavlovian response to certain expressions. As soon as you hear GCD, you should be thinking of the Euclidean algorithm. So by Euclidean algorithm, there exists U and V such that UX plus VP equals 1. But X and P are in J, so UX plus VP is in J, so 1 is in J, therefore what does J have to equal if 1 is in J? It has to equal Z. Because remember, if you're an ideal, if you take any element in the ideal, you can multiply by anything in the ring, and you must still be in the ideal. Once you show the multiplicative identity is in your ideal, the ideal has to be all of the ring. If multiplicative identity in ideal, ideal is the entire ring. That's a great fact to know. And so what we've just shown is that if we take a prime and look at the ideal generated by the prime, there's no ideal that's strictly larger. But if I take a composite number like 12, I actually found several possibilities. And so this becomes an interesting question. When can I have a larger ideal that contains my ideal? Always, just take the ring. Okay, when can I have a larger ideal that strictly contains my ideal and is not the entire ring? And that's not always going to be possible. And so over here, this leads to what we'll call maximal ideals and prime ideals. So let R be what type of ring? Commutative. I'm probably not going to be able to get that by you twice in class. R is going to be a commutative ring. An ideal I of R is a prime ideal if I does not equal R, and whenever we have a product of two elements, A times B is in the ideal, then either A is in the ideal or B is in the ideal. This should remind you a lot of something we've had before when we were looking at just regular integers. This is if a prime divides a product, and I think I referenced the paper I wrote with Professor Silva. So if I give you two numbers and I multiply them, and the prime divides the product, then either the prime divides the first or the prime divides the second. What kind of OR is this? There's two types of OR. So if a prime divides AB, then either P divides A or P divides B. Does anybody know what kind of OR that is? What the two types of ORs are? It's the inclusive OR. It could divide both. I could give you, 6 times 4, and the prime could be 2, and 2 divides both. I don't want to go into the details while this is being recorded. When I was in college, I was put on bad academic standing, and I had to quickly add a class for distribution requirements. I took a class on baby logic, and the professor slipped up on the exam, and she gave us, 10 sentences for half the exam, like P and Q implies not P, if and only if not, stuff like that. And the instruction stated, state which of the following sentences are true or false. And technically, each sentence is truth value determinable. Each sentence is true or false. She was not amused. Well, she was amused, but she said she would have flunked me if I had actually done that. You need to think about what or are you using. When we say P divides A or P divides B, we are not excluding the case that P could divide both. We just know it has to divide at least one, but it might divide both. Sometimes you want a situation where only one happens, and you would say it's the exclusive or. P divides A or P divides B, but P does not divide both. For us, what we're doing, it's going to be the inclusive or. So this is in some sense a generalization of a really nice property that the integers have. If a prime divides a product, the prime divides at least one of the factors. We have seen situations where this is not true. We looked at cosine x times cosine x is 1 minus sine x times 1 plus cosine x. And so you have some kind of strange situation. And the question is, well, what is cosine? What does it mean to be a prime element when we're now looking at rings of polynomials, rings of trigonometric functions? There are ways to try to generalize these notions from the integers to these more general settings. Okay, so this is right now just a definitional slide. R is a commutative ring. An ideal I is called a prime ideal if it's not all of R. And whenever we have a product of two elements that's in the ideal, either the first or the second term in the product is in the ideal. This is a nice generalization of a prime number. And so a prime number goes to a prime ideal in some sense. We also have the following nice consequence. If you take two numbers, neither of which is an I, then clearly their product can't be an I if I is a prime ideal, because by definition, a prime ideal is such that whenever a product is in, at least one of them is in. So the next definition, definition 340, is let R be a commutative ring. An ideal I is called a maximal ideal if I is not equal to R, and there are no ideals properly contained between I and R. So in other words, if I have some ideal J which contains I and is contained in J, then there's only two possibilities. J equals I or J equals R. So for example, if R equals Z, then give me a maximal ideal. Or give me infinitely many maximal ideals. So infinitely many maximal ideals. Any ideal generated by a prime. Then any ideal generated by a prime, oh, I don't know how it became. Then P for P prime is maximal. Give me a non-maximal. I'm sorry, 12, or give me infinitely many non-maximal. One is not prime. So anything that's composite. So if I take any mn for mn greater than or equal to 2 is not maximal. And what we would have is the ideal mn is contained in the ideal m, it's contained in the ideal n, and both of those are contained in all of z, and these are not equal. And so these are going to be examples of non-maximal ideals. Okay, we've done all these examples here already, so I will just end with the following slide and then make some comments. So let R be a kind of ring? Commutative ring, okay? So we will only be considering commutative rings, but we've already seen now that this is actually a little bit of a restriction. Is we might want to study matrices. And unfortunately, when we lose commutativity, every definition we've had here right now is now out the books. So let R be a commutative ring and let I be an ideal where I does not equal R. Then I is a prime ideal if and only if the quotient ring R modded out by I is an integral domain. So what does it mean to be an integral domain? Yes, so it means there's no zero divisors. So if I look at a clock, 3 is not 0, 4 is not 0, but 3 times 4 is 0. If I have a clock with a prime number of hours, then it will be an integral domain. And then I is a maximal ideal if and only if the quotient ring is a field. Well, now you can probably see why they don't want to take I to be R. If you take the integers and you mod out by 1, so 2 integers are equivalent if they differ by 1. What does your clock reduce to? Every integer is the same, so what would it reduce to? Yeah, which identity? The additive. So the clock would just be the element 0. And it's really not that interesting to study 0. And you have to worry sometimes that your definitions might be a little bit off if you have situations that you only have one element. If you have a ring where you only have the 0 element, the multiplicative identity could be the same as the additive identity. 0 plus 0 is 0, 0 times 0 is 0. So if you multiply anything by 0, you get back that element. 0 functions as a multiplicative identity if your set is just the 0 element, right? This is a really bad situation. So we don't want I to be R. We don't want to mod out so that we make everything the same, right? I'm trying to understand some object in the universe. Let's consider everything to be equivalent. Well, no. The idea is to try to figure out which properties really matter. One of my favorite examples is when Galileo was doing his experiment in physics. He was trying to see if two balls of different masses will drop in the same amount of time. Has everybody heard of this experiment? Okay, good. What were the colors of the balls? Are you sure? Does it matter?
Either way.
Does it matter? Does color matter for this experiment? Probably not. Imagine I have one that's black, one that's white, and I have them outside in the hot sun for 8 hours. They could now be at different temperatures. And so the color may not matter initially, but it could lead to them being at different temperatures. So if I kept them at the same temperature, I don't think the color would matter. And for Galileo's experiment, we would say two balls are equivalent if they have the same mass and the same temperature and the same radius. That might be my equivalency. I won't care about color. I may not care about what material they're made out of, so long as they have the same mass. But maybe I care if the mass is uniform or not. If it has uniform density, or if maybe more of the mass is concentrated in the center. Could that matter? So these are all the different things you want to think about, is we want to try to reduce things to equivalence classes. And so the idea is, if we want to understand a complicated object like a ring R, we take an ideal which is smaller than I, which we can hopefully understand. And then we break understanding R into two parts. We first understand I, and then we look at the smaller ring R mod I, where we say two elements in R are equivalent if they differ by something in I. And so I is the prime ideal if and only if the quotient ring R mod I is an integral domain. I is a maximal ideal if and only if the quotient ring R mod I is a field. And then the last corollary 3.44, every maximal ideal is a prime ideal. Okay, so this is a good place to stop for today.